I've got y equals sine x up on the board here, and I've made a note that it is not invertible, because I can see it definitely fails the horizontal line test. If I draw a horizontal line at any y value between -1 and 1, this graph is going to intersect it infinitely many times. So what I'm going to do is I'm going to create a related function. It's going to have the same formula, y equals sine x, but it's going to have a different domain. I'm going to restrict the domain. So I'm going to restrict the x values that I can plug in to my sine function so that I get something that's 1-to-1. Now, as I do that, and I try to figure out how I'm going to restrict the domain, I'm going to be looking at this picture over here, but I'm also going to be thinking in terms of quadrants. Quadrant 1, 2, 3, and 4. Notice that on this graph, we've marked off our quadrantal angles because those are sort of the important points on a graph of sine. This interval from 0 to pi over 2, that interval corresponds to angles that would be in quadrant 1 if I were representing them rotationally. The interval from pi over 2 to pi corresponds to quadrant 2 if I were representing things rotationally. Obviously, I'm not saying that if I'm here, I'm over in this quadrant 2. I'm saying if instead of representing my angle as a point along the x-axis, I were representing it as a rotation, it would land in quadrant 2. And then this next interval is 3 and 4. And of course, over here, from -pi over 2 to 0 is also quadrant 4. So as I restrict the domain, what I want to do is pick an interval of x values that corresponds to 2 quadrants worth of angles. One quadrant where sine takes on its positive values, and one quadrant where sine takes on its negative values. Now, as I do that, I'm going to be strategically lazy. So the easiest quadrant to work in is quadrant 1, and in particular, the version of quadrant 1 that includes angles between 0 and pi over 2. So I'm going to keep that portion of the graph, including that endpoint there at pi over 2, 1. Now, that gives me all of the positive values that sine can take on. So I want to make sure that I don't repeat those at all, but I don't have any of the negative values that sine can take on. So I need to choose another interval that corresponds to a quadrant of angles where sine takes on its negative values. I'm going to immediately rule out quadrant 3. I'd like an adjacent quadrant because I'd like to choose a continuous piece of the graph, a nice connected piece of graph. So I'm always going to want to choose either 2 or 4. Now, if I chose quadrant 2, sine would be repeating its positive value, so that doesn't seem so good. So that's out. Looks like we're choosing quadrant 4. But I don't want this version of quadrant 4 because then I'd have this huge gap in between my two pieces. I'm going to choose this version of quadrant 4 because that's adjacent to the version of quadrant 1 that I'm keeping. So if I keep the interval from -pi over 2, that's a negative sign there, from -pi over 2 to pi over 2, I get this graph. This is the same as the sine function when it's defined. It's just not defined for angles bigger than pi over 2 or smaller than -pi over 2. But this function is invertible. So with that, I can now define what is sometimes called the inverse sine function. So that can be written two ways. It can be written this way, like so. I'm not crazy about that notation. Or it can be written this way, arcsin of x. I like that notation better, so that's what I'm going to use. But they are both correct, and you may use either form of notation. The reason I'm not crazy about this is because that is an inverse sine it is not an exponent. Okay. So, sine inverse of x is not the same as sine x to the -1. With other powers, like if I'm squaring something, I can put a 2 there or there and they mean the same thing. With a -1, when I put it there, it means inverse. Sine x to the -1, that would be the reciprocal of sine x. That's cosecant of x. That's very different. Taking the reciprocal and switching the roles of x and y are not the same thing. So if you're at all likely to confuse that, I recommend that you go with this name. Okay, y equals arcsin of x. Okay. Now what that means is that, oh, I forgot to finish writing this down. I'm sorry. This function that I defined here was y equals sine of x, but with the restriction that x was between -π/2 and π/2. That's what made it invertible, is restricting that domain. So the inverse function is going to be x equals sine y, but y is between -π/2 and +π/2. Okay. So I'm switching the roles of x and y to define this new function. Okay. All right, excellent. So with that definition, I can start actually trying to evaluate this new function that I have. Okay. So let's say I wanted to evaluate arcsin of -1/2. Okay. Now, what I usually like to do is give that a name that reminds me that it's an angle. Okay. Because with trig functions, you plug in an angle and you get out a trig ratio. With inverse trig, you plug in a trig ratio, you're going to get out an angle. That's the other reason I like this name arcsin, is that the way we define the radian measure of an angle is it coincides with the arc length that angle intercepts on the unit circle, the signed arc length that we get. So that makes me think angle, to remember that the output is an angle, because I'm so used to angles being my inputs. Okay. So what this means, by giving it a name, I can now say this means that sine of theta is -1/2. But that's not all it means, because if I just write that, that equation has infinitely many answers. I also need theta to be between -π/2 and +π/2. So figuring out what theta is basically going to be a two-step process. Just like evaluating a trig function is usually a two-step process, I look at what quadrant it's in to figure out the sign, and then I use the reference angle to get the absolute value. Well, here I'm just going to do that in reverse. Sine of theta is -1/2. Well, that makes it a negative number. But I know that I'm working between -π/2 and +π/2. So I've got to be in either quadrant 1 or 4. If sine is negative, I'm in quadrant 4. Okay. But I have to be careful, because I'm not getting into quadrant 4 by rotating that way, because then I'd have a big positive angle. I'm getting there by rotating this way. So my theta is going to be a negative acute angle. Okay. I now want to figure out what my reference angle is. So there's my reference angle alpha. And what I know about alpha is that its sign will be the absolute value of -1/2, which will just be 1/2. And alpha, the reference angle, is always a positive acute angle. So now I can say, what angle do I know? What acute angle do I know whose sine is 1/2? If I draw my 30, 60, 90, I can see that sine of 30 degrees is 1/2. Now, when we're working with inverse trig, we're working in radians unless explicitly told otherwise. The definition is in radians unless you are told to work in degrees. So it's 30 degrees, but I would convert that to radians. So alpha would be pi over 6, but I can see I want theta to basically just be the opposite of that, because I'm going to rotate that amount, but in the negative direction. So this would be negative pi over 6. So instead of using the quadrant to get the sine, I'm using the sine to get the quadrant. And then, instead of using the reference angle to get the trig ratio, I'm using the trig ratio to get the reference angle. But I'm still doing that two-part thing where the quadrant and the sine go together and the reference angle and the absolute value go together. Okay, excellent. So that's our first time evaluating an inverse trig function. We'll practice a little bit more of that in the next video.